Hi there. Welcome. It's Chem Coach Powers, and we're going to be learning about stoichiometry today. Stoichiometry is a fun word to say, and it's a fun thing to do. Basically, the idea behind stoichiometry is you're taking all of the stuff that we've so far learned about balancing chemical equations and mole to mole conversions and mass to mole conversions, all that kind of stuff, and we're putting them all together. And we're basically showing you how you can use these mathematical formulas to quantitatively tell you how much of one thing you will get if you start with a certain amount of this other thing. So anyway, that's what stoichiometry is. Let's get going. Let's have some fun as we do this. Our objectives today, we're going to cover two sections, 9.1 and 9.2 in our book. And so we're going to determine the mole and particle ratios from a balanced chemical equation. And we're going to, criteria for success here, if I give you a balanced chemical equation, you can tell me the mole ratios for any two substances involved in that reaction. Now, this part is super easy. We're going to be able to breeze through this part really quickly. So remember that stoichiometry comes from the Greek stoichion, which is the element, and metron, which is to measure. And we have two types of stoichiometry, one that you've already done. This is the composition stoichiometry, where you can talk about the mass relationships between the different parts of a compound, for instance. And so you'd say, oh, well, the compound of water, H2O, has 88% by mass of oxygen and 12% by mass of hydrogen. That's the kind of idea here. The composition stoichiometry, just dealing with the percent compositions of a particular compound. And then the thing that you haven't done yet, which we're getting to do now, is reaction stoichiometry. We'll look at chemical equations, and we're going to figure out the mass relationships between the reactants and the products in that chemical reaction. So remember that anytime we're doing a stoichiometry problem, we've got to start with the balanced chemical equation. Start with what? Balanced chemical equation, Powers. Yeah, that's right. All right, so reaction stoichiometry is going to be based on the ratios of the coefficients. We've talked about the coefficients. You can change coefficients if you're balancing an equation, but you can't change the subscripts. We've talked about the fact that those coefficients are actually connected to volume when we talk about gases, and they're connected to the number of moles, right? So not just the number of particles, but the number of moles and the volume. And so if we were to balance this following equation, and we have hydrogen and chlorine coming together to make HCl, we would throw in some numbers in here, right? So we'd have to have a 2 in there, and these would both be 1s, right? So if we balance that, now that 1, 1, 2, that now explains to us or describes to us the relationship of the gas. In this case, we could talk about volume, we could talk about moles, we could talk about particles. Okay, so particles, moles, and volume. As long as it's a gas, you can also talk about volume. If any of those little parts aren't gas, then we can't talk about that part with regard to it. So if we had this sentence, we wanted to fill in these blanks, we could fill in the blanks with any of these things, right? We could put particles in each one of these. One particle of hydrogen plus one particle of chlorine gives you 2 particles of hydrogen chloride or hydrochloric acid. Then you could also throw in moles, right? 1 mole of hydrogen plus 1 mole of chlorine gives you 1 mole of hydrochloric acid. Or you could throw in the volume. We could say 1 liter of hydrogen or a milliliter gives you 1 liter of chlorine, or a milliliter gives you or yields 1 liter of hydrogen plus 1 liter of chlorine yields 2 liters of hydrochloric acid. So this is the way you would be able to do this. You can substitute any of those in there. All right, so remember that you can be dealing with the reactant side, you can be dealing with the product side, you could go from the reactants to the products, it can involve any of those relationships. It's just going to compare 2 of those. That's what these reaction stoichiometry problems are going to be doing. Now, this is also called the theoretical yield calculation. Stoichiometry is dealing with the theoretical amounts that we're going to be getting, right? And so we can go from moles to moles, from moles to mass, from mass to moles, or from mass to mass. We can use any sort of calculation between any of these different types of our reactants and products, right? And so what is a mole ratio? Remember, the mole ratio is going to look at the coefficients, assume that they are moles of the substance in a balanced chemical equation, and then we can just make a ratio out of those. So for instance, if I have this aluminum oxide and that is decomposing to give us aluminum and oxygen, I can use that 2, 4, 3. I can use these little mole ratios, I can use these coefficients to create a mole ratio. So I can talk about the relationship between these, or the relationships between these, or the relationships between these. Like I can talk about a lot of different relationships here, right? And so if I were to talk about the mole ratio of aluminum oxide to aluminum, I would use 2 to 4, all right? Or I could reduce that down and say it's a 1 to 2 relationship. So you can go ahead and create mole ratios for all sorts of different combinations within a balanced chemical equation. All right. And so what are we doing? Why are we doing this? Well, we're using it to link or to show the relationship between those two substances in our calculations. And we're going to use it in our problems, right? We're going to solve problems with these relationships. Okay, so now your turn, right? Can you balance the following equation? Yeah. And then can we write all the possible mole ratios? All right, so I want you to pause it and practice real quick, come back and see if you get it right. And welcome back. All right, so when you balance this, you saw immediately that we had 2 chlorines on this side, so we probably have got to get 2 chlorines and then 2 hydrogens on that side. So now it's balanced. Now what's our mole relationship, right? We can talk about what that mole relationship is by looking at each and every one of those situations. We can say 1 to 2 for magnesium to hydrogen chloride, 1 to 1 for magnesium to magnesium chloride, and 1 to 1 for magnesium to hydrogen. You can also flip-flop those. And you can talk about the relationship that they are if you just reverse them, all right? So you'll notice that, well, we got 4 things here. We haven't even flip-flopped them yet. We got 2 moles of hydrogen chloride for every 1 mole of magnesium chloride. Okay, so what basically we're doing, we're just going through. This is magnesium and hydrogen chloride. So this is the relationship between these two. This is magnesium and magnesium chloride. That's the relationship between these two. This one is magnesium and hydrogen. So that's the relationship between these two. This one is hydrogen chloride and magnesium, so that's the relationship between these two. I haven't done that one yet. And then this is the hydrogen chloride and the hydrogen, which is a relationship between these two. And again, like I said, you can flip-flop each of these, and so you could theoretically say, hey, there's 10 different ratios that I could create from just this balanced chemical equation that I could use in a problem, for instance, okay? Oh, sorry, and I forgot one of them, didn't I? Where's the last one I forgot? Oh, yeah, look at it right here. Magnesium, chloride, and hydrogen. All right, so 12 different ones. So you've got 6 here, 6 different mole ratios. And then if you wanted to reverse those, then you could have 12 total mole ratios that could be derived from just that one balanced chemical equation. Okay? All right, so we're going to skip through that catalyst, and we're going to just jump right into 9.2. So that covered 9.1, and if you want to go back to that little screen, rewind a little bit, you want to practice that catalyst, you're welcome to. But we're just going to jump into our 9.2 objectives. To solve these ideal stoichiometric problems involving moles, mass, or numbers of particles in a chemical reaction. So if your criteria for success, if I give you an amount of one substance in a reaction, you'll be able to calculate the amount of the other substance. Now, this could be, I could give it to you in moles or grams or particles. I could give you 2 reactants to try to figure out between, or I could give you a reactant and a product or 2 products, right? You're going to be able to use these mole conversions and the mole ratios to figure out what you need to make those reactions convert, right? All right, so let's say, what kind of types of problems might I give you? I might give you a problem where I give you the moles and I ask for the moles, okay? That would be considered a mole-to-mole problem. All right, so lots of different types of stoichiometry problems where we're going from mole to mole or mass to mole or mole to mass or mass to mass. Well, if I give you this problem type where I give you the moles and I'm asking for the moles, we call this a mole to mole conversion. And this would be what our mole road looks like. Remember how we talked about the mole road? This would be like that mole road. We're just going from moles of A to moles of B, or we could go back and forth the other way, right? It's not hard. All we have to do is write out what we start with. Always on a stoichiometry problem is we've got to balance our equation, make sure it's balanced. Once that's written, we know what our unknowns and knowns are, then we're going to create conversion factors. You don't have to create these ahead of time. You can create these on the fly as you go through and do your unit conversions, right? Just know how those conversions work. You put up that dimensional analysis problem, and then you'll just solve it, right? Calculate it and get your answer, check your work, ask to see if it makes sense. So let's say if we have an example here. We've got lithium and oxygen reacting explosively to form lithium oxide. How many moles of lithium oxide will form if 2 moles of lithium react? Okay, so we can again see what's our given and what's our unknowns, right? So it's giving us 2 moles of lithium, so that's a mole that it's giving us, and it's asking us how many moles of lithium oxide, and so that's our unknown. So we're asking to go from mole to mole. So what do we start with? Always start with what you're given. You're given the 2 moles of lithium, and you're going to try to go to lithium oxide. Always start with your balanced chemical equation. So how in the world did I know that? Well, remember, you are coming up with that based upon the words here, right? It says lithium and oxygen react. So you've got to be writing out your lithium and your oxygen, and it's going to form lithium oxide. How do you know it's Li2O? Remember that oxygen, some of this is review, right? Oxygen has a 2 negative charge. Lithium has a 1 positive charge. And so we would be crisscrossing those, right? And so that's why that 2 comes down there, and we end up with the Li2O. And then where did the 4 and the 2 come from? Well, you had to balance your equation, right? So if I have Li2 here, and I have an Li here, and then I have O2 here and an O here. Oh, I probably need to make a 2 in front to make my O's, and now that's doubled my lithium, so I need a 4 in front of my lithium. Now you start with what you're given. What are you given? You're given the 2 moles of lithium. So that's what you start with. So as you start your problem, you want to start it with the 2 moles of lithium, okay? Now, what mole ratio are you going to need? You're going to need the ratio that takes you between lithium and lithium oxide, right? Because that was the given and the unknown. Here's your given, here's your unknown. And so you need to figure out the ratio, and you got that from here. There's 2 moles of lithium oxide for every 4 moles of lithium. You're going to use that then in this problem. And you're going to say, all right, well, if I start with my given 2 moles of lithium, what do I want on bottom? I want my moles of lithium on bottom so that they cancel out, right? And now I put on top the 2 moles of lithium oxide. Why? Because that was the ratio that I made, right? I made that ratio here from my balanced chemical equation, and that's why I used it here. So what am I left with? A lot of times I like to circle what I'm left with, make sure that's what I was looking for. I'm looking for moles of lithium oxide. Indeed, that's what I've got. So then I can come up with my answer. Don't forget, we want to box our answers, right? So my answer is 1 mole of lithium oxide. We have to ask ourselves, does that make sense? So do this little, mental thing in your brain. Does it make sense that I end up with a mole of lithium oxide if I start with 2 moles of lithium? Well, yeah, it makes sense. Why? Because if I start with 4, I get 2. Therefore, if I start with 2, I should get 1, right? It's that same ratio. 4 to 2 is the same as 2 to 1. So that's going to make sense. All right. Now, you can try this, okay? You can do a little pause and practice and see what you do. Disinfectant hydrogen peroxide decomposes to form water and oxygen gas. How many moles of oxygen will result from the decomposition of 5 moles of hydrogen peroxide? All right, so pause this and practice and see how you do. And welcome back. And here's your answer. You got to start with a balanced chemical equation. Hopefully you came up with that. Now, what are your givens? 5 moles. That's what you'll start with when you actually start your problem, right? And then your unknown is the moles of oxygen. So you start with 5 moles of hydrogen peroxide trying to find moles of oxygen. You know that your conversion factor is the 1 to 2 ratio from the balanced chemical equation. So you start here. 5 moles of the hydrogen peroxide, and then you use that balanced chemical equation. Sorry, it's a little bit offset there. And you'll get the answer you're looking for, which is 2.5 moles. Ask yourself, does that make sense? Well, yeah, because if I start with 2, I end up getting 1. So if I start with 5, I end up getting 2.5. I'm basically getting half the amount. That makes sense. Sweet. All right. Now, all the rest of the reactions that we're going to do in stoichiometry are just adding a mole conversion that you've already done. So we're adding the conversion of the molar mass from the periodic table, for instance. So everything is cake. This is the only part that we hadn't yet done yet, was taking those little mole ratios and putting them in to our calculation. Now we're just going to be adding on to that basic mole to mole. So it's all easy from this point. It's all stuff you've already done. So the part that's new, the part that we just did, was this little part there. Why was that new? Well, we've done moles to mole stuff before, but we haven't taken the mole ratios from the balanced chemical equation before. So now we're taking that mole ratio. And so that's the part that's new, even though we've already done mole to mole conversions. Now we're taking them from the balanced chemical equation. And so now we're just going to be doing stuff that we've done before, where we take moles to mass and mass to moles. So it's going to be easy. That's the full map of everything you need to know. Mole to mass and then mass to mole calculations are going to be just a portion of that, right? So let's say if I'm doing a mole to mass or a mass to mole calculation, so I'm not going from mole to mole, I'm not going from mass to mass. I'm doing the other parts, right? So if we go back to this little part, I'm going either from mass to mole, or I'm going from moles to mass, right? So yeah, it's getting kind of messy. I'm doing a portion of that. So I'm basically got a couple step problems. But these are easy, same type of basic setup. Start with the balanced chemical equation, figure out what your knowns or unknowns are. And you can do the conversion factors ahead if you want, but again, you can just do them on the fly. That's not a problem. Do your problem and make sure that your units are canceling. If you go through and just make sure units are canceling, then you don't really have to set up your mole conversion factors ahead of time, right? All right, so here's our problem. This is a mole to mass. When sodium azide is activated in an automobile airbag, nitrogen gas and sodium are produced according to the following unbalanced chemical equation. So we've given you the equation here. Now you just have to balance it. I've got 3 nitrogen on the one side, 2 on the other. I better probably change that, right? All right, so if 0.5 moles of sodium azide reacts, what mass of nitrogen would result? So you can see that we're going from the given moles and we're trying to figure out the unknown mass, all right? And so first we got to balance our equation. That's our first problem, all right? So we do that, lowest whole number ratio. If we can get that least common multiple, we'll end up with 2 of the sodium nitrides. Why? Because 2 times 3 is 6. That gives us 6 nitrogens, and 3 times 2 is 6, gives us 6 nitrogens. So that balances out once we get that other 2 in there. And again, we can write out those mole ratios ahead of time if we want to, but we really don't need to. All I need to see you doing is this part here, right? Just do the step by step. 0.5 moles of NaNO3, NaN3. Just make sure that your moles of NaN3 are going to be down on the bottom of this next one. They cancel. Now, it's very important at this point that you don't jump and start going to mass already. If you start with moles of one substance, the NaN3, then you have to go to moles of another substance. Okay, it's really important on that mole-to-mole, that mole-mole road, right? You showed you that mole road, and we had moles of A to moles of B. Make sure that you do not try to jump directly from moles of A to mass of B. Okay, you've got to go through the moles. That's why it's called the mole road. Now once we get moles of B, we can go to mass of B, but don't skip that step. You always have to go from moles of A to moles of B. Whatever you're starting with to whatever you're trying to get to, you've got to go through those moles when you're doing these types of problems. And so that's where I use my mole ratio. And then I use this. Where do I get that number from? I get that number from the periodic table, right? I go on the periodic table and I say, oh, well, nitrogen is 14.01 grams per mole. And of course, I've got N2, so I've got to double that and I get 28.02. So that's where that number comes from. And then you just calculate. 0.5 times 3 divided by 2 times 28.02 gives you 21.0 grams. Now, very important here, it's not shown here, but very important in your work that you're actually showing the N2. So there should have been an N2 up there. Definitely needs to be an N2 there. Don't forget those little elements. That's really important, okay? All right, so now it's your turn. You've got carborundum, which is SiC. It's a hard substance made by combining silicon dioxide with coke. That's carbon, okay? It's basically, think of it as coal. In the following reaction, SiO2 plus C gives us SiC plus CO. All right, you got to do this. You're going to pause and practice and come back and let's see how you do. All right, you've balanced your chemical equation, right? Oh, my goodness. Well, that's about all you could have done is the balanced chemical equation. I forgot to give you the mole part. Now the next part, you're like, what? I've got 2 moles of carbon, and I got to figure out mass in grams, okay? So I've gone from my given moles of carbon, and I got to figure out the grams of SiC, right? So given and unknown. So your balanced chemical equation, boom, you've got that one. All right, now you can pause and practice again, see if you can get the other part of the answer. And you're back. Thank you. All right, so then this is what the other part of the answer would look like. Basically, we start with our given, right? We started with 2 moles of C, and we used our mole ratio here, that 3:1 from our balanced chemical equation, and we went to the periodic table. Something missing over here, okay? We got to make sure this is written out, and it's not written out right now, but SiC, 40.10 grams of SiC, and then you just calculate that out. Boom, 26.7 grams. There's something missing here. Don't forget to have the actual values, SiC, written there as well, okay? Silicon carbide. All right, that's how you do those. Now, let's do the next type of example. This is mass to mole. So that one, we went from mole to mass. Now we're going from mass to mole. So we started with a mass of A. We've got to go all the way to the mole of B. But we're not doing mass to mass yet. That's one more step beyond. How many moles of aluminum will be produced from 300 grams of aluminum oxide in the following reaction? give us the reaction. Sweet, let's balance it. Let's start with our givens. And again, do you need to do this step here and write that out? No, I don't need you to write that out separately. You're going to just put it into your problem. Just show me one big, long problem. That's all I really need. So what am I looking for? I'm looking for that. You give me that. That's all I need, okay? You don't have to give me all that extra. Just show me that I've got grams of aluminum canceling out with grams of aluminum, moles of aluminum, sorry, that's aluminum oxide, moles of aluminum oxide canceling out with moles of aluminum oxide. And look, I went from moles to moles with my balanced chemical reaction. And so I went from grams of A, right? This was the grams of A. Excuse me. Then I went to moles of A. And now in this step, I went to, and I got my moles of B. Okay. So answer, and at least this time we've got the actual element written out, 5.88 moles of aluminum. Box it. You're done. Not bad, right? All right. Your turn. How many moles of NO are formed if 824 grams of ammonia and excess oxygen are used in the following reaction? There's your reaction, and they've given you the given, okay, 824 grams of ammonia. Which one is ammonia? This is ammonia. And how many moles of nitrogen monoxide are formed? So that's what you're looking for, okay? So we're going from grams, that's mass, to moles. All right, pause it and practice. See how you do. Come back. Boop, you're back. Yay. All right, here's what you would have done. That should have been your balanced reaction. Then you would have shown it like this. And you would have gotten that from the periodic table, got that from your balanced chemical reaction, 4NH3 to 4NO. And then you would have gotten your answer, 48.4 moles. Ah! We're missing something here. What are we missing? We're missing our NO. No, we're missing no. Okay, box it. Make sure that no is there. All right, nitrogen monoxide. All right, so you're figuring this stuff out. Now let's go from mass to mass. Massive A to massive B. It's the mole road. We got to go along the mole road, travel through moles to get there, right? So all the way from mass to mass. This is what we use typically in a lab, and so this is the most useful, the most common way that we'll do things, because we aren't usually given moles in a laboratory. We're usually given the mass of one thing, and we got to figure out how much mass of the other thing am I supposed to produce, okay? Or if I want to get X amount of this in my final reaction, how much of this other stuff, this starting ingredients, do I have to actually start with? We use this stuff all the time in the chemistry laboratory. So again, steps, nothing different here. No, notice that your steps are going exactly the same. It's just that you're going to have 2 molar masses that you have to deal with here instead of 1, right? So you've got to have that mole ratio, and you're going to have both molar masses. All right, so here's our example. We start with our laughing gas and a balanced chemical equation. Laughing gas and water are produced when ammonium nitrate is decomposed. Did you know that laughing gas was a really common drug in the 18th century? I think in the early 19th century too. They would actually, when they first discovered this gas, they were like little dens where they would all go and get high on laughing gas. And today we just use it in the dentist's office. But yeah, that was a real big common drug back when they first started making laughing gas. Anyway, sorry, distractor. So we're trying to figure out the grams, right? So here's our unknown is how many grams of ammonium nitrate. Okay, so we want to know the grams of that one to produce 33 grams of N2O. Okay, so maybe your science teacher says, I need 33 grams of N2O. And if you don't have it, we can't do this other experiment. So I need you to go figure out, produce it, go produce it. And so you're like, what? So here's your balance, here's your reaction. You've got to balance the reaction. And now you've got to figure out how many grams you have to start with. All right. So first thing you've got to do is you've got to balance it, right? Is this thing balanced? Well, we got a 2 in front of it. So let's see. We got 4 hydrogens, 1, 2 nitrogens, 2 nitrogens. We've got 3 oxygen. We're balanced already. Sweet. All right. So now we just have to do our conversion factors. Remember, we need 2 of our conversion factors from the periodic table, right? And so we need it for both of our substances. And now, and again, do you have to do that on a separate step? No, I don't need that on a separate step. You can just throw it out here just like this, and that's all I need. All right. So once you do this, then make sure that everything cancels and that you get your final answer. Again, make sure that grams of ammonium nitrate, which is what you're looking for, is what you got, right? So you start here with grams of dinitrogen monoxide, and now you've got grams of ammonium nitrate. Sweet. That's where I wanted to go. That's what I got. Don't forget to box your answer. And you are golden. You ready to try it on your own? I know you are. All right, here we go. Mass to mass practice. When a copper metal is added to silver nitrate in solution, silver metal and copper 2 nitrate are produced. What mass of silver is produced from 100 grams of copper? Okay, should you be able to figure out that equation on your own? I think so, right? Copper metal, that's a little solid there, is added to silver nitrate. And this is a solution, so it's aqueous. And what's going to happen? Well, the silver metal as a solid is going to come out, and then you're going to have the copper 2 nitrate. And so copper 2 means it's got a 2 charge, so that's got to cross down. And I've got copper 2 nitrate as a solution is going to be produced. So now I've got to balance that. I've got 2 nitrates here. I've only got 1 nitrate here, so let me throw a 2 in front of that. And let me throw a 2 in front of that, and now we're balanced. You see what we're doing? So you should be able to do that. And here in this case, we've shown you that equation, and we've got it all done. And now you've got to do the steps. And again, all you got to do is worry about showing me the work there. That's the work I need to see. You get your final answer. What's it forgetting? You are so bad because you are not putting your stuff on the end. Silver is what we're getting, right? And then it's boxed. All right. How'd you do? Did I tell you to pause? I forgot to tell you to pause, but I'm sure you did that, right? You paused it and tried it on your own. Oh, I showed you the answer. So horrible. All right. Well, guess what? You get to try it again. Here's your extra ticket. Okay. One last time. Try this. See if you get the answers. And then, yeah. So pause. And we're back. Okay. Balanced chemical equation already done for us. If you see a number out there in front of that, we've already balanced it for you, right? So you don't have to do that part. It says 0.37 moles of Cl2 reactant excess chlorine. How many moles of HCl are produced? A lot of people get confused with this word excess chlorine. It just means that it's not a limiting factor, and you haven't learned about that yet. That's going to be in the next unit, right? 9.3. So we'll talk about that in our next lecture, but it just means that you're starting with the other substance, all right? We're just starting with the ones that we've been given, 0.37 moles of chlorine. So we start with that 0.37 moles of chlorine, and sure, what do we have to have on bottom? All right, we want to go to moles. So we're just going from moles to moles. Sweet, this is easy. So I just have to have my moles of chlorine on bottom. There it is, 1 mole of chlorine on bottom. And then we're going to HCl, so 2 moles of HCl on top. Boom, 0.74 moles of HCl. How hard is that? Okay, 0.74. Boom, done. How many sig figs? 2 sig figs, sweet, 2 sig figs, all good. Make sense? So easy. All right. If 2 grams, 2.0 grams of hydrogen react with excess chlorine, what mass of HCl is produced? Oh my goodness, I'm going mass to mass. All right, well, that's not a problem. We know how to do mass to mass now. All right, so I start with 2 grams of H2. And if I want to go from mass to mass, I have to go through the mole road, so I've got to convert to moles. And so I have to say, well, I know this. Go to the periodic table. There's 2.02 grams of H2. Periodic table, right? For every 1 mole of H2. Now I've got to use, now I'm in moles of H2. I've got to go from moles of H2 to the mole of the other thing I'm looking for. In this case, it's HCl. Where do I go? I go to my balanced chemical equation. It says that 1 mole of H2 is good for 2 moles of HCl. And now I go to my next step. And so now I say, okay, well, for every 1 mole of HCl, how many grams of HCl do I have? Well, remember, Cl is 35.45, I think. So plus the 1 of hydrogen gives me 36.45 grams of HCl. Could be wrong on that. Didn't look that up. So if I'm wrong, forgive me. So now we go through and we do our work here, right? So we plug it into our calculator. Oh my goodness, where'd my calculator go? All right, popping up a calculator on my computer. Pop. popping up. There it is. So 2 divided by 2.02 times 2 times 36. I hope I'm right about that. 0.45 equals. And if I'm wrong, you're all laughing at me right now. Powers, you're so crazy and so stupid. You should just look it up on the periodic table. And I think to myself, no, I can figure it out. I know it on my own. So 72, I've got 2 sig figs here. And so I've got 72 grams. I want 2 sig figs on the final one of HCl. You think I got it right? I hope so. If not, that's just sad. All right. There we go. La, la, la. Now you know how to do it. Okay, so what have we learned today? Can we solve ideal stoichiometry problems involving moles, mass, or number of particles in a chemical reaction? Yes. Now the only thing I didn't go over with you was that number of particles per se, but remember that that's just that one additional step, right? So if I wanted to go to my number of particles, my dust just popped on me. Then if I were at moles, right, then I could do a mole conversion to my number of particles. Remember, for every 1 mole that you have 6.022 times 10 to the 23rd particles, right, whatever it is. So if I needed to go to the particles, I just need to add that step in. Easy, right? All right, and then criteria for success. Given an amount of one substance in a reaction, if I give you any of those, then you can calculate the amount of any other substance using the mole ratio, other needed conversions. Thank you for listening. Please ask me any questions you might have. I'll be glad to help you. You have an awesome day. God bless you, and be kind to one another. See ya.